Hello everyone, I am an avatar created by Yili Lin, a doctoral student in health services research at the Department of Health Administration and Policy, George Mason University. In this section, I'll be introducing you to selecting a well-fitting regression model for data. Before diving into modeling, thoroughly understanding your problem and the data you're working with is essential. Define the objective. What exactly are you trying to predict or explain? Is it a continuous outcome or a categorical outcome? Dependent variable. This is the outcome you're trying to predict, like disease risk or test scores. Independent variables, predictors. These are the features that influence the outcome. This could include demographic data, behavioral data, environmental factors, etc. Data types. Ensure you identify the nature of your variables, numerical, categorical, ordinal, etc., as this will impact your model choice. Linear regression is designed for numerical outcomes, but for binary or categorical outcomes, you might need logistic regression or multinomial models. Measurement units and scales. Are all your variables measured on comparable scales? For instance, income may be in dollars, but age in years, and these differences could distort the model if not handled properly. The key questions you may ask yourself in this step: what are your independent and dependent variables? Is there a clear, plausible relationship between them based on theory or previous research? What is the distribution of your outcome variable, normal, skewed, count, binary? Exploratory data analysis lays the groundwork for model building. Proper data cleaning and understanding ensure that your model will be accurate and reliable. Handling missing data. Use techniques like mean, median, mode imputation, or multiple imputation depending on the nature and mechanism of the missing data. Feature engineering. Sometimes raw data may not capture all relationships, so you might create new features such as ratio, log transform, polynomial terms. Encoding categorical variables. Convert categorical variables into numerical representations using methods like one-hot encoding for nominal categories or label encoding for ordinal categories. Exploratory visualizations. Scatter plots for continuous variables to identify possible linear, nonlinear relationships. Box plots and histograms to check distributions and outliers. Correlation matrices and heat maps to identify multicollinearity among independent variables. A high correlation suggests that two predictors may not provide independent information. In this step, ask yourself that, are there any outliers that could distort the model? What is the relationship between the predictors and the outcome? Are the variables normally distributed or do they need transformation, like log, square root? The simplest model should serve as your baseline for comparison. Often, this is a linear regression model without any interactions or transformations. Fit the simple model using a formula like this. Evaluate the baseline. Use R-squared to assess the proportion of variance in the dependent variable explained by the independent variables, but note that higher R-squared does not always indicate a better model. Check the residuals to ensure no obvious patterns exist, indicating model misspecification. This step gives you a starting point to compare more complex models. Regression models have several underlying assumptions that must be checked to ensure the model is valid. See details in the other sessions. Once you've established that a simple model doesn't capture all relationships, it's time to increase complexity step by step. Interaction terms. Sometimes, the effect of one independent variable on the dependent variable depends on another independent variable. For example, the effect of exercise on weight loss might depend on the person's diet. To account for this, interaction terms can be added to regression models using either a star or a colon. When working with a large number of variables, generating interaction terms manually becomes inefficient. R functions like combine and interaction help automate the process of creating all possible two-way interaction terms. This approach can be particularly helpful when dealing with high-dimensional datasets, though you need to be cautious about multicollinearity and overfitting, as these can become problematic with too many interaction terms. Polynomial terms. For nonlinear relationships between predictors and outcomes, you can use polynomial regression. Add quadratic or cubic terms. Transformations. If your data has skewness or non-normality, you can transform the variables. Log transformations for right-skewed data. Square root or inverse transformations for count data or reducing high variance. Modeling techniques. Depending on your data, consider using alternative methods. Generalized linear models, GLM, useful when the dependent variable is not normally distributed. Please transit to the second part for the rest of the information.